answers to that question. I suspect you'll hear a few during these upcoming presentations, but I'll give you my own. And that is, well, there's no doubt that we are entering a great transition in the energy industry as the world decarbonizes, with a lot of disruption in the industry. At the same time, every projection for how this transition will occur indicates that oil and gas are going to provide a lot of energy, maybe even the most source of energy during at least some part of this transition. So as the transition happens, we'd like to understand how the oil and gas industry can adapt to this era of decarbonization. And today we'll hear three different opportunities about that from our three panelists. So we'll start off with the first one today. Our first presentation is from Murray Reed. He's the CEO of QLM Technologies. Murray is an applied physicist by background, and he's been involved in the development of many technologies. Today, he's going to talk to us about a new technology that will allow the industry to detect fugitive methane emissions. So Murray, please take it away. Murray, it looks like you might be on mute.
All right, yeah, well, there we go. I had to unmute myself. Someone muted me, but that's okay. Thanks, thanks, Drew. Very much appreciate. Thanks, Lou and Ray, and all the organizers of this conference. I mean, it's a great cross-disciplinary symposium on obviously a vital topic. So I've really been enjoying the talks, and I'll try and entertain you for half an hour. Let me try and share my screen. And go big screen as well. So it always takes longer than you think. There we go. All right, at least from my perspective, it looks good. Let me know if it's not from yours. So as Drew said, I'm the CEO of QLM Technology, and very much appreciate the opportunity to share the work we're doing. QLM is a startup in Bristol, and we're developing a new type of accurate long-range and low-cost infrared gas camera that can see and measure invisible greenhouse gases. And we're building these into systems that we think will enable the automatic and continuous monitoring of all the greenhouse gas emissions from all the industrial sites in the world. So that's a bold claim, so wait and see how we go. Where we're starting is methane, because it's the second largest source of climate change, and obviously a much more potent greenhouse gas than CO2, and it's been getting a lot of press lately with the administration's recent changes. But there's still a lot of potential, obviously, because methane has a short lifetime. If we stop the methane emissions, we can have a rapid effect. And it's a big problem. There are approximately 1 million active gas well pads in the world, and just as many industrial sites. And as the press will tell you, they're all leaking much more than was suspected originally. And so under this pressure, all the oil and gas majors have pledged to reduce emissions. And I'm happy to say, as someone in Britain, that BP is one of the leaders. But you can't manage what you can't measure, and no one is measuring methane properly. So the existing leak detection involves traditionally local sniffers. So that's something handheld that you carry up to the leak. You can imagine that's fairly time consuming. It's moved on in the last 10 years to infrared cameras, which can actually see the leaks, but they're very expensive. They still need trained operators to interpret, and they can't actually quantify how much the gas is leaking. So you still have to, after you've seen it, you have to still walk up to it with a sniffer. So in these conditions, basically, the regulations are set up so that you only have to do 1 or 2 inspections a year, or even less, as of a couple of days ago in the US. So the vast majority of total emissions are due to what are called super emitters that are not detected for months at a time. And the industry has recognized it has a big problem, even if the administration hasn't. And the industry is looking for really practical ways to effectively implement continuous automatic monitoring and get away from intermittent and unsuccessful monitoring. So, you know, I'm not from the oil and gas industry. I know a lot of people in this symposium aren't directly either, or even from the really the greenhouse emissions industry altogether. But we think we've got something to contribute, and I wanted to just explain where we do come from, so you get an idea of why we think we're capable of helping. We've founded this company in something called the Quantum Technology Enterprise Center in Bristol, which is a spin out of the University of Bristol's Quantum Technology Group. And my co-founder, the picture here is Zhao Ai, got his PhD there in electronics and quantum technology, and particularly quantum photonics. And this is a rich tool set, and he has really thought a lot about this over the last 10 years. And in fact, was a principal scientist on a CO2 monitoring satellite system. So you can probably see the overlap, basically a camera in space looking down at CO2. He left the university and went out to industry and was working on what's called acousto-optic sensing of gas leaks, and realized that what he already had invented or thought about was much more practical than what was being deployed. So he came back and joined our enterprise center, which is an incubator. I was there as a mentor. We've got together and formed this company. My history goes back to Stanford, so I do recognize the photos that Mark was showing. I got my PhD in the 80s, and since then, for 30 years, have been working developing products, profitable, successful products for the semiconductor manufacturing and telecom industries based on photonics. So I'm very much a semiconductor laser guy, and have 30 years dealing with people like Intel and Agilent and Apple, to name just the ones that start with vowels. And this is a tough industry. So I think together, I've got the understanding of how to build practical products, and Zhao's got a really brilliant idea. So we've got together, and let me tell you more about it. But first of all, since I know everyone's a little geographically challenged, even I don't think I knew exactly where Bristol was before I came over here 5 years ago. I always wanted to give you a map and a bit of a picture of where we're coming from. Bristol's about 2 hours on train due west of London. It's a lovely part of the country. The university is next to the River Avon, and you can see we have a historical bridge or two. And really, it is the leading city behind London. London dominates everything, but in digital technology and vegan food. So we're most famous, I think, for things that you might recognize as Banksy and Wallace and Gromit. And recently, actually, we got quite a bit of press because we got our Titan of the slave industry statue and threw it in the river. Long overdue. So it's a great town, very pretty and very smart, and you should come and visit us if you get a chance. I'm also just going to give you a quick introduction to optics, because I'm not going to assume, given how multidisciplinary this conference is, that everyone knows what I'm talking about, and I don't want to lose you too quickly. This is fairly obvious, I hope, and actually my graph is not very accurate in terms of the spectroscopy, so it's just representational. Greenhouse gases are, of course, invisible, and they don't absorb visible light. It's definition. But they do absorb infrared light, and specifically different gases absorb very specific different colors or wavelengths. And so this is how you can see a greenhouse gas. Methane, for example, the one that I'm going to talk about the most, but the same applies to CO2 and carbon monoxide and many others. And we're already working on those as well. But methane absorbs at a wavelength that's 1651, which is in what's called the shortwave infrared. Now, infrared cameras also measure the same sort of wavelengths, of course, and they can detect infrared light and gas, and they can therefore see the gases, just pretty much like a visible camera can see smoke. And you can see here a picture of an infrared camera looking at a plume of methane, and you can see it looks just pretty much like smoke. But you can also see that as a camera, it's not a narrow spectroscopy. It's not a selective device. And so it sees a lot of other things at the same time, and other gases at the same time. And in particular, again, like a normal camera and smoke, you may be able to see smoke, but you can't measure exactly how much smoke is there. So cameras are great for seeing things, but they're limited in terms of real practical use. The way to measure gases, at least one of the most successful ways to measure gases, and been around for quite a long time, is to use a laser, and that's my background. Lasers will emit a single wavelength, but you can also get a laser that can be tuned. So you can get a laser that moves backwards and forwards in wavelength, and it doesn't have to move backwards and forwards very much to go across these gas absorption lines. And here's a picture of the actual gas absorption line of methane and our tuning across it. And with this, you can measure exactly how much methane's there, because the depth of that absorption, how low that peak goes, tells you exactly the quantification of how much methane the laser has passed through. So this something else that we're using here, and again, I know I'm you know, basically taking it back to basics. So LiDAR cameras, but I'm surprised how many people don't understand LiDAR. So LiDAR is a laser light detection and ranging. And what you're doing is taking a laser and sending it out and letting it bounce off the surroundings, and you pick up the echo back. So LiDAR is actually a follow-on from radar, originally radio, in the same words. And by scanning the laser around and looking at those reflections, you can build up a picture. And the picture here is one of autonomous vehicle LiDAR. And there's been billions of dollars spent on autonomous vehicle LiDARs in the last few years, as you're probably well aware, as people try and implement these as practical systems. And they've got a lot smaller and a lot more practical than they used to. So this is a typical example these days. And actually, this is quite a large one. It's no longer a giant thing on top of the car. It's becoming something that's much more practical. And we're using exactly that sort of technology ourselves. So we're really leveraging this activity. And now the way to do it is put those two things together I just described. You put a tunable laser together with a LiDAR. Normally LiDAR for a car is just looking at what's out there. They want to see that they're not going to hit something, so they're looking just at the solid objects. But if you also tune the laser at the same time, you can look at the data you get, and you can figure out what gas is in the line that the laser has traced out. And here's a picture of a what's called a differential absorption LiDAR system from our friends at the National Physical Laboratory. That's the NIST of the UK, and they've deployed this, and they're all over the world. But you can see it's a massive system. And in fact, it sits in the back of a semi-truck and they drive it around everywhere. And that's really what tunable diode LiDAR cameras looked like until we came along. And we've therefore made a big leap forward in terms of the technology by using what are called single photon avalanche detectors. Now, that's somewhat self-explanatory. Single photon means you detect single photons, and the way you do it is you create an electron avalanche inside the semiconductor. It's a solid-state device with appropriate structures, and they're quite complicated to make this work well, because the trick is you want a lot of avalanches in a hurry. You want the avalanche to reset so you have gigahertz output. And they're effectively digital devices because a single photon just creates a burst. It's a Geiger mode, like a Geiger counter. The ones we're interested in are the ones with long wavelengths. And there are silicon SPADs, been around for quite a long time, but the long wavelength indium gallium arsenide SPADs, which are actually developed for quantum fiber optics, are much more recent. And they've got the great ability, as far as we're concerned, to see the gas lines. So this allows us now to use single photon quantum technology to go do gas measurement. And that's exactly what we've done. We've put this together into our methane camera. And so this is a new type of infrared LiDAR using the novel SWIR SPAD, and that allows us to use a very low power semiconductor laser, a telecom laser. It's got the wavelength appropriate, 1651, as I described, and the beam, the very low power beam, goes out and back, and with the SPAD you measure what's going on and scan it around. Since it's a laser system, it's very sensitive to methane, so we can measure parts per million. It's accurate, a few percent accuracy is typical. And because it's single photon, it's very long range. So single photon isn't much light. Of course, it's about as low as you can get. And that's what we're seeing. We're seeing picking the signal out of this signal photon stream. And that means we can see more than 100 meters. And really the figure of merit for a camera is how little, a gas camera, how little gas you can see and how far away you can see it. So you want to have long range and high sensitivity. And that's the combination that we get with this system. So the picture on the right shows our engineer Chris, and in front of him is a prototype, one of our prototype cameras. You can get an idea for the first version size, and trust me, it's going to get a lot smaller. And then it's looking down on a scaffolding that was set up by our friends at the National Physical Laboratory with an artificial leak, a deliberate methane leak. And what you can see is we create a picture, an image of the methane pouring out of that leak. We can see exactly where it is, and we can also see where the wind is taking it. So this is a precise measurement. As I say, we're down to peak parts per million. It's actually, what we measure is parts per million times length. It's a concentration path length product is the right phrase. But the interesting thing is, if you want to go fast, you can take a relatively crude picture, but then once you see something interesting, you can stop, you can zoom in, and you can scan it around for a little while, and you can really build up a precision measurement. And of course, a gas leak's not going very fast, so you can sit there for a while, in a minute or so, and build up a very high resolution and high precision measurement, which is the mode we expect to be operating in and are operating in. Really, we can see above the methane ambient. So the graph on the right is our measurement out to 200 meters, and what we're looking at is no leaks at all, just what's there. The background ambient of methane is 1.8 parts per million at the moment. It's steadily rising as the decades go past, and so what we should see is a straight line with that slope, and that's effectively what we do see. A little bit of noise because some things aren't reflecting as well as others, but basically we can use this to measure methane above the background from 10 meters to 200 meters. And for leaks, what you want to know is what's above the background. It's really not necessary to know what's below the background because it's not really having any effect on the big picture. So here's a couple of 100-meter demonstrations. First at NPL, who we've been working with for 18 months or more now. And this is not zoomed in. So, it gives you an idea of how far away 100 meters is, which is, anyone who's done any athletics knows how far that is. It's quite away. What we've got against that back wall, which is at 100 meters, because we've got the LiDAR picture below the camera picture, and so you can see the 100-meter calibration, is a small pipe, the same sort of leak that I showed in the previous picture. And you can obviously identify it, and you can actually size it, and it stands out very clearly above the background in the bottom picture. Now, if we zoom in, which is very easy to do with a laser because you just change the raster scan, now we can start to identify exactly where things are. And so this now is a picture on the right of 3 balloons, and they're hard to see because they're clear balloons. And we put one of them we filled with methane. And so what you can see is the methane stands out very clearly. The others have nothing in it. And that's a demonstration of our ability to locate. So we don't just play with balloons. We've done industrial qualifications and industrial trials. And here's a few pictures from a trial at Total in France. And this is, again, artificially plumbed leaks, but they were blind, so they didn't tell us what they were, and we had to come back and tell them where they were and what they were. And you can see the sort of images that we get even in complex industrial situations. And the interesting thing about LiDAR is it's a 3D technique. You're measuring the total concentration in a path. So if you integrate that, you can get a mass flow. You have to include the wind speed in the calculation. And that actually gives you most of the noise, because it turns out the wind is not something that's actually very well controlled in most situations and varies around in structures like this. But we still get very accurate measurements of the total leak rate. And that's important because people really care about the total leak rate. They don't care about the methane in the air. They want to know, is the leak bad enough that I have to go fix it because the rules tell me I have to fix it? So we've got great performance, I hope you can see, but there's a much more important side to the story, or maybe equally important side to the story. And that is, this isn't a science experiment anymore. This is ready, and we're starting to turn it into something that's really industrial and practical. The components, I've broken them apart here. I'm not going to get into the details too much, but the bespoke piece is the transceiver. That's a kind of gold box thing you see. And this is a photonics assembly, a hybrid photonics assembly of the style used in telecom. And that's exactly what we're using, telecom packaging. The rest is really almost off the shelf. Of course, the electronics is custom, but what we're using is autonomous vehicle scanners, and that's exactly what that picture is of the optics there, and security camera hardware. So really, this is a gas security camera. You can look at it from that perspective, and we obviously include a normal security camera with it and pan tilt it around, and we can get all that hardware from mature existing reasonably high volume industrial use already. So that means we kind of have a leg up in terms of pricing. The other thing is, this is practical. It's a LiDAR system, and if a LiDAR system can work at 200 kilometers an hour on the Autobahn on a Mercedes, I think you'll agree it can probably work pretty well in a relatively static industrial situation. So it works in all weathers, it works in any time of day, and in the complex environments that you see. But probably just as important, it's low power. The single photon detection means this is a low power laser, and low power means there's eye safe. These wavelengths are eye safe anyway, but this is intrinsically actually class 1, which is about as safe as you can get. But more importantly, it's battery powered and Wi-Fi powered if you want it to be. And we've actually put our units on a drone and flown them around. And I'll talk more about that later. But as I said, these are all fairly simple stuff, quite frankly. The beauty's in the algorithms. And so this will scale down in cost. And that's where we're going. And that's why this has the potential to be a ubiquitous, continuous automatic monitoring system. And why I say not just methane, I say all greenhouse industrial gases, because like security cameras, it's really a price volume curve. If you can get them cheap enough, they'll put them everywhere. And we think we can get this technology cheap enough. So this is a little bit of description of just how the sort of steps, and the biggest part of it is integrating the transceiver. We're on the sort of path that everyone knows for a cell phone camera. We took a Hasselblad and we turned it into a cell phone camera. And we're probably not going to go that far because we don't want billions of these. Well, maybe we do want billions of these. You guys, have to tell me that. But that's the technology path. And so this price scales down very rapidly with volume, and even with a few thousand, we're starting to have significant reduction in price with the existing design without getting into automation and real integration, which obviously has, as I say, cell phone camera abilities to eventually scale. So our position in competition is healthy because we've got the performance in terms of accuracy and range that's the sort of performance you've only been able to get out of much more expensive and size, weight, and power intensive units in the past. And we have a trajectory to keep driving that price down. So, we're ahead and we're going to keep ahead. And we think this enables automatic continuous monitoring. Our IP position is also healthy because Zhao spent 10 years thinking about this, I'm happy to say, and he's really got it. He really understands how to do it. It's actually a difficult synthesis of tunable diode laser absorption spectroscopy, which is fundamentally an analog frequency domain, and single photon lidar, which is fundamentally a digital time domain technique. And blending those together, if you're an electronic engineer, you probably realize those are different languages. So, we've got a really strong start on the algorithms, and we've got a really strong start on the integrated photonics. That's my background, and we have a lot of help with that. There are no current patents that restrict our freedom, and we have a broad architecture patent pending both in the UK and PCT. So we continue to develop SPIDS and our new algorithms, and we've got mid-IR versions going as well. But as I said, the algorithms are really the secret sauce, and that we're keeping as trade secrets. Just to touch on the SPIDS, because they are so critical, and there's a long way to go. So we're by no means tapping this out. You can see that as a risk or an opportunity. I personally see that as a huge opportunity. The SPIDS we're using at the moment are solid-state semiconductor devices that are 3% efficient. If you know anything about solid-state semiconductor devices, that's woeful. That's truly woeful. And it can easily be 10 times better than that. And we're evaluating units that should take us there relatively quickly, both from China and the US. And we're working with government funding in the UK with Sheffield University to develop new designs. The schematic on the bottom there gives you some idea of the structure, complexity to make these things work, to drive these avalanches in rapid turnover. It's a complicated MBE growth and processing, but in the end, once you can do it, you get a lot out of a wafer. So it's a very rich area for us. And as I said, we've had strong UK government support. I'm happy to say the Innovate UK is the funding body over there that deals with industrial strategic funding, and we've been funded through the Quantum Technology Program. Slowly, it's not overwhelming amounts of money, but we're now up to the point that we've got a 2-year program with all the partners in the bottom graph or graphic that we're working to make a robust product demonstration over the next couple of years, and we're well engaged in that already. The end users in our consortium that we're working closely with are National Grid, BP, and Amatec, and they all want this. So we have industrial traction, we have pull. I'm not going to talk too much about that because some of that's confidential, but let me at least give you a quote. And this one's from Peter Droigmiller, who's the Director of Innovation and Technology at Amitec. And Amitec is a $5 billion a year process and analytical instruments manufacturer who does a lot of non-contact instrumentation for industry. So, this is a very credible source. Quote, QLM's gas imager technology demonstrators have achieved detection levels that are remarkable. I believe that as products, these will allow our industry to move from intermittent scheduled inspections to much more effective continuous monitoring, a major step forward. And I'm happy to say it's not just Peter who believes that. We are getting more and more response. And really why I'm here is to spread the word. And we're looking for people who are interested in this sort of performance and interested in helping us move it forward. We have partners, as I said, already that are helping us. And so this just gives you some idea of the technology underpinning. It's not just me and Zhao. We have mature contractor engineers and partners to do both the photonics and the electronics and the software, the firmware. This is experience in instrumentation, in telecom and in downwell oil and gas technologies that is all in Bristol, I'm happy to say. So as I say, Bristol's a powerful workhorse for this. Our target products are the basic security camera, as I've described, and there's some specs. This is sort of sitting on a pole and looking around. It can be installed or it can be moved around, reinstalled every day, basically, without any trouble. The more interesting one, and where we started in some sense, and we really will come back to, is getting these mobile, fast and portable and smaller. So first of all, we're making them rugged and solid because that's what the industry wants and needs. But the potential is to make these small and cheap and light and put them on drones and put them in hands and really turn them into useful things for a whole bunch of applications. And I just want to touch on drone deployment because we have done that. And of course, there are multiple sorts of drones and people are very interested. It's a very active field. We've put our initial sensor on the octocopter that you can see. And this is a hexacopter. It's a DJI M600 for those who know drones. But what we found is that UAVs are still a challenge because they're subject to restrictive laws and they have still have significant weight, power, and flight time limitations that make them less than ideal for highly pragmatic environments. There's still a lot of skepticism from the oil and gas industry about them, though they have started to use them. And we want to be on the leading edge of that. So we're working with multiple drone system developers, and particularly autonomous drones, which remove the cost of the operator, and tethered versions, which remove the flight time limitations, are very interesting directions that we have got conversations going with. We've also got pull. National Grid very much wants to replace their helicopters. So they do a visual flight check of their entire national transmission system every fortnight. Every 2 weeks to translate. And they're very interested in moving to something that's more pragmatic than that. So the other thing that obviously everyone would realize in this industry that's very pragmatic and hanging over us all is the regulations and the fits and starts and regulations. The interesting thing is that the Method 21 is the original sniffer regulation, and it's now been updated to some degree to allow optical gas images, optical infrared cameras to come in with something called Quad OA in the lingo. Interestingly, these all have kind of crazy requirements in terms of technical leak measurement standards. They set the bar at a level that's a fraction of a litre per minute. We typically think 1 litre a minute is overkill. And the reality is 90% of emissions, as indicated by this study from Brandt and et al. At Stanford, 90% of emissions are above 60 litres a minute. So mandating a fraction of a litre per minute is a great barrier to entry, but it's not a practical way of improving things. Thankfully, the regulations are being written and have been written such that they're talking about reductions of total levels rather than specific sensitivities. And so, I think, and Bob will speak more about this, I think there is change coming, and we can fit into these regulations. Our customers don't seem to be as perturbed as maybe we are. So to wrap up, gas cameras for all industrial greenhouse gases. I mean, this is what we think we need. As I said, you can't manage what you can't measure. And if COVID hasn't taught us anything, it's that, I hope. So it needs to be security camera systems. It needs to be drone camera systems. It needs to be handheld, and it needs to be methane and carbon dioxide and everything else that you want. And we've got all that. We have got a carbon dioxide version already. I didn't mention that, but we are pursuing other gases. And we really think that this will have a meaningful emission reduction if industry gets under control. And if you don't watch it, I have doubts it will get under control. So to wrap up, we have gas images that are accurate, sensitive, long range, and crucially low cost, and will get lower cost, and that will enable widespread automatic continuous monitoring. We've got a good consortium going, but we don't have that much money. We're raising more money. So if you're interested in helping, or you're interested in the research and validating our images in specific use cases, please contact us. Thank you very much for your time.
Thank you very much, Murray. We've got a couple of questions lined up in the Q&A box, but before I get to this, I wanted to squeeze in one on my own. So you mentioned the recent changes in the regulation, and I wanted to ask how those impacted technology. In particular, the idea of regulating VOC in terms of methane. I've heard that some technologies have difficulty measuring VOCs because of the spectroscopy, essentially because the line is so broad, it's more or less impossible to scan over it. Can you talk a little bit about what the impacts are and whether systems that are designed for methane can work as well for VOC given the difference in the spectroscopy?
I'll only say a little, because I think the next speaker, Bob, is much more qualified to talk about this than I am. In terms of impact, as I say, we look through our customers and our potential customers, and we're not seeing a lot of concern. I mean, yeah, the regulations are to some degree viewed with, I don't know, what's the right word? Well, they're respected, but they're not respected a lot, I guess is the right way to say it. Because there's a lot of fungibility in them. There's a lot of flexibility built into them in terms of proving a system works properly as opposed to a device works properly. But yeah, it's a major concern for us in terms of spectroscopy. No, we can't see multiple gases. Again, it's a bit of possibly thrown up as a bit of a barrier to entry in that the cameras intrinsically see broad swaths of color, and therefore look at broad absorption bands. Where we are, because we think accuracy is more important, quantitative accuracy is more, we're honing in on our spectroscopy, and that limits our ability to see widely everything that's out there. However, methane is obviously a big problem, and methane's therefore big enough for us for the moment to worry about. But if the old regulation that concentrated on VOCs as opposed to methane, and if it goes back in that direction, it does make things confusing. My understanding is there's a lot of methane that comes along with all the VOCs anyway, so it's kind of we're not seeing it as a major stumbling block just yet. But obviously, regulation has to be rational, or it's not going to work properly.
Very good. Thank you very much. I appreciate taking the time to sneak in a question for me. So let me go now to the questions from the participants. So I'll start off with the first. If you could, the first one is asking about the retroreflectors. So if you could pop back to the first image, it says, in that first image you showed a gas leak. It was a smoke-like cloud of methane. There was no background to reflect the LiDAR signal there. How would you measure that specific type of leak, and would you need to measure it from a higher vantage point in order to reflect the LiDAR on the ground?
It's a really good point, and this is why drone deployment was the original vision, and that's exactly right. LiDAR systems, as the questioner has pointed out, require a back reflection, and that's why in our pictures you'll see we are looking from elevated points. But if you're looking at 30 meters away and we can get a reflection from 200 meters away, you don't have to be very elevated to still see something in the background. And what we're finding is most industrial environments have a lot of stuff around, really, that we can see, and we can see reflections from a long, long way away. It is a problem if you've got an elevated pipe, exactly as he described, that first picture with the camera where the smokestack's going up in the air. But it's a problem for the cameras too, because the background there is even less calibrated than normal. So they can see what's up there, but they can't quantify it very accurately. We can not see it unless we have something behind it. So we don't use the sky as a back reflector. And that's why we're very interested in the drones. But in the short term, our customers are happy to put it in elevated masts and elevated situations and look down like a security camera normally looks down. You get to see more normally from an elevated position anyway. So that works for everybody.
Very good, thank you. Next question is about geographical applications. So the question asks, I want to know if developing economies, especially in Africa, with incessant methane leaks from pipelines, currently adopt this kind of technology? And if not, what are your plans to introduce the technology on a global scale?
It's a great question because there's more and more emissions from developing countries, obviously, and more it has to be an economically sensible deployment. And this is why we're obsessed about cost, and we believe cost is absolutely crucial to make this a success and have a meaningful effect on emissions. But cost is a price volume curve, and you don't get there on day one. And so we're starting with high value applications in more developed countries with people like Amatec, who have got specific, they're interested, for instance, in methane reforming, monitoring, and that's a great high value application. But it's a virtuous cycle, and the technology will scale down in price. And once it's down at a few $100s, and I should point out that the autonomous car lidars are currently priced at the ones that we buy at £500, so $600-800, and those are that's too high a price. They are continuing pushing them further and further down. So we'll be on that same curve, and I think at a certain point it becomes absolutely appropriate for the whole world.
Very good, thank you. So that actually leads into the next question, talking about some of the technical specs, and maybe you can answer this in terms of also how you think those will scale with volume. But the question asks, what is the weight of the device, and what is the area coverage of the detection range?
Well, I mean, we keep improving it, but the prototypes were less than 2 kilograms. And we're now in the process of building the next ones, and they could see 100 meters in radius, or 100 meters on a side, I guess, if you want to make things simple, however you want to do the math. I don't think I'll multiply the math myself, but 100 meters distance in all directions. If you put it on a 360-degree pan tilt, then it's a 100-meter radius circle, and as I say, a couple of kilograms. The interest is for drone deployment is to get that lower and lower, of course. But it's a trade-off, because the biggest weight component in the end becomes the telescope that does the projection and the capture of the light. And that's kind of, there's a size distance trade-off there.
Very good. So the next question gets into more of the conversion from ppm meters to liters per minute. Yes, does the device assume a transport model like a Gaussian plume when quantifying the emission flow rate?
We have used a few different models, and the Gaussian plume is one of the most popular ones. There are much more complicated ones that people have shown us and we've played with, but those calculations were actually done with none of those. Those were done with a straight integration and an assumption of a uniform wind field, which it ignores buoyancy altogether. So this is why we've got the 20% accuracy type thing. We talk to customers, and that's good enough. I mean, they're used to order of magnitude accuracy estimates, and so there's a certain point where it's in the error bars, and they're happy with it. But absolutely, developing the algorithm to go from a methane concentration path length image to a accurate flow rate calculation, that's something that's ongoing. And it's funny, everyone thinks they have their own better way to do it, is what we've found. So we keep it simple and let other people run with it if they want to. But we have one software guy who's working on it.
Very good. So just a couple more questions there. Another one about challenging gases. Question reads, can you use the same principle to image hydrogen gas?
Not really. But hydrogen's one of those, the diatomic molecules are a bit tricky. Oxygen has a bit of an absorption. Hydrogen has obviously elevated temperature hydrogen in the sun, obviously the classic Rybud spectra. But no, I mean, it doesn't have absorption in the range that we're dealing with. what we're most interested in doing is moving out to longer wavelength from where we are. At the moment, as I showed in the initial SPAD picture, we've got a kind of a wavelength cutoff with these devices, and they're practical room temperature devices. So, you know, they're what we want to use. We don't want to use superconducting crazy stuff. That cuts off at 1.7 micron, 1700 nanometers, and that limits us to greenhouse gases, really. The next one we're looking at is ammonia, but people are very interested in heavier gases, particularly xylene and things like that. You know, the petrochemical industry obviously has a lot of uses of methane, but it also produces a lot of interesting gases that need to be monitored. And not greenhouse particularly if they're heavy, but they have spectroscopy that's amenable to the 3 micron range, and this is where mid-IR is a very active area for us and a very active area for everyone else. There are lasers now that are work out there, but the single photon detectors do not. We have configurations that don't actually need single photon detection. We can still use the same technique with higher flux rates. We don't get quite the same range, but we do get measurements. So it's an active area, but at the moment we're concentrating on the shortwave IR. Thank
you. And then last question. What about interference from other atmospheric gases like water vapor?
Well, absolutely. I mean, this is something you have to watch for, basically. And the picture I showed of the gas lines was absolutely, it's unscientific at a high level. The reality is there are a lot of gas lines throughout all these spectral regions. And what you have to do is pick them carefully. And it's a long history of people doing this, and this is why we've got this methane line, because there are a dozen methane lines, and that's the one that's been interfered to not have been selected not to have the interferences. And you have to worry about CO2, you have to worry about water, you have to worry about carbon monoxide, and a lot of other things really that all could be there in significant different applications into significant amounts. And but it is an established art, and there's something called HITRAN that you can look up pretty directly and figure out what you really want to pick. And we're not, this is an old, it's been around for a while. So the wavelengths are fairly well known.
Excellent. Well, thank you very much, Murray. Really appreciate the fantastic presentation. Also, we are right on time, so we'll move